Welcome, and thank you for joining us for our water webinar, Open Channel Flow Measurement 101. If you have any questions during the webinar, please utilize the chat or Q&A functions within Zoom. All questions will be answered at the end. This webinar will be recorded and a video will be made available in the next few days. Our presenter today is Darrell Kuta, Flowmeter Business Development Manager. With that, I'll turn it over to Darrell.
Hello, and thank you for joining me today on the Open Channel Flow Measurement 101. I am your host, Darrell Kuta, and I will be talking to you today about different level and flow meter technologies. So let's begin. Which flow measurement technology should I use? Today I'm going to talk about the different sensor types that are available, where they should be used, the different technology on how they operate, and what are the advantages and disadvantages of each sensor type. So some of the sensors that you're going to see, we'll talk about the level sensors to start with, will be the ultrasonic level sensor and the radar level sensor, which are non-contact sensor technologies. And then I'll discuss the bubbler level sensor and also the submerged probe or pressure transducer. So what's unique about the different level sensors? We'll start with the ultrasonic. So as far as an ultrasonic sensor, it is a non-contact sensor. It has an ultrasonic transducer that transmits a sound wave, bounces off the surface, which could be the water, and it detects the echo. So it reads the level as a function of time. So we have a transmit and a receive transducer, and it measures the amount of time it takes to hit the water surface and come back to determine what the distance is to your water surface. And with that, the level can be calculated. Now, all ultrasonic sensors have a deadband. And why do they have a deadband? Because each sensor takes a certain amount of time to be able to transmit and then turn around and receive that signal. And so some transducers have a 1-inch deadband, others have a 1-foot deadband. So it just depends on which sensor you purchase. Now, all ultrasonic sensors have temperature sensors, and the reason they have temperature sensors in them is because it needs to use the air temperature to calculate the speed of sound. Now, what are the advantages and disadvantages of an ultrasonic sensor? The advantages are it's non-contact sensing, which makes it easy to install because you're mounting the sensor above your flow stream so you don't have to stop the flow, which can make that easier to install. And being non-contact provides minimal maintenance. It doesn't mean there's no maintenance. It means there's less maintenance because it's above the flow stream. It's less likely to be affected by debris. However, debris could be in the channel, which could create a problem. So you will need to occasionally clean out your channel. Now, the disadvantages are the deadband. Depending on your application, you may have limitations on how high you can mount the sensor above your flow stream. So that could restrict or depend on what type of sensor you're going to install. If you have a low headspace above your water, or if you have a lot of headspace, you can use different types of non-contact sensors. The beam angle, that is a disadvantage because if you have a very narrow channel, the beam spread is going to be different on the different ultrasonic sensors, but there's potential that it could hit these side walls, which then could give you false echoes and read the distance of the walls instead of the water. Now, in most cases, that can be corrected by entering in a minimum and maximum blanking distance to tell it to ignore those walls that it may be hitting. Wind could also be a problem with ultrasonic sensors because we are transmitting a sound wave, and the wind can actually take away or reduce the return signal. Think of it as when you're outside on a windy day, you have to speak much louder to somebody so they can hear you because the wind is actually carrying away your sound waves. Steam can also be an issue because the ultrasonic sensor will reflect off of the water particles in the air, which could then give you an incorrect level reading or reduced signal strength. Foam can also be a problem because it will minimize the ultrasonic signal strength, and it may actually absorb the ultrasonic sound wave, thus giving you an error. Now, turbulence can also be a problem because with an ultrasonic sensor, we're looking for a return echo, which would normally bounce off of a flat surface to get the strongest return signal. If we have a lot of surface turbulence, that's going to reduce your signal strength. Now, radar sensors, they operate in the same fashion as far as they transmit a radar signal, which bounces off the surface, and it's a function of time to determine what that level is. Radar sensors are commonly found in tanks. They're used in river monitoring applications because they usually have a greater distance than an ultrasonic sensor. But they can also be used in most every application that you can use an ultrasonic sensor. So what are the advantages? It's still non-contacting, minimal maintenance because it is above the flow stream. And the biggest advantage of that is the greater distance. So they could be mounted on a bridge. You know, I've seen specs on the radar sensors where you can mount them up to 100 feet away from the water. So they do have a very large range for the radar sensor. Now, the disadvantages is that it has that large nose or antenna on there. So that's going to require more space depending on your application to install it. Surface turbulence, it has the same issues that you would see with a ultrasonic sensor. It likes to have a nice smooth surface to get the best return signal. And the cost of a radar could be more than a ultrasonic sensor. And in some applications, the installation could be a little more difficult to install the radar sensor. Say if it's on a bridge, there's a little more logistics on trying to install it than trying to install it over a flume. Now let's move on to the bubbler. How does a bubbler operate? So a bubbler is an air pump, which then builds up air pressure into a tank, the accumulator, and then the air is released through a control valve. Usually the air bubbles come out at a rate of about 1 to 2 bubbles per second. And what that does is then the transducer measures how much pressure it takes to push one air bubble out. And that will determine what the water level is. So the advantages of a bubbler, suitable for small channels, whereas the ultrasonic is worried about the hitting the side walls of a narrow flume. The bubbler does not have that issue because it's usually a 1/8 inch bubble line that's mounted in the bottom of your channel. It is not affected by wind or steam or foam. Or even temperature and turbulence because it's under the water and it's just measuring how much pressure is above the end of that bubble line to read your water depth. And only the bubble tube comes in contact with the flow stream. The advantage of that is that if something were to damage the bubble line, it's inexpensive to replace that vinyl bubble line, or you may even have a stainless steel bubble tube. So we have no electronics in the flow stream, and so if you did have to replace your bubble line, it's usually fairly easy and inexpensive. And as far as you'll find that the accuracy of a bubble level sensor is very similar to an ultrasonic sensor. And as I mentioned before, the bubble line is inexpensive to install. Now, the disadvantages is that you could possibly have restrictions in the bubble line, or if you have sediment that builds up over the end of the bubble line, that could possibly give you a false high level. Some bubblers, like the ISCO signature meter, have a built-in purge system, so if it senses that there's debris over the end of that bubble line, it will automatically send out a burst of air to try to free up any restriction on the end of the line, which could lead to the higher maintenance. Since you do actually have something in the flow stream, there is a potential for some debris to get caught on the bubble line. And greater power consumption, because we have a physical motor that is running to build up air pressure, it will require a little bit more power to operate the air pump. Now, the air pumps do not run continuously. They build up air pressure, shut off, and then as the air bleeds out, then the compressor turns back on for a few seconds. Now let's move on to the pressure transducer. We have a differential pressure transducer, which most pressure transducers are vented to atmospheric pressure to give you reliable and accurate level readings. The advantages of a pressure transducer is they're suitable for small channels. They're not affected by wind, steam, foam, or turbulence because they are below the water surface. And the pressure transducer, the one thing I like about them is that if it does get covered with sediment or silt or sand, it's still able to read that positive pressure over the top of that sensor. Now, what are the disadvantages? Well, since we have electronics in the flow stream, if there are chemicals in the flow stream, it could actually break down the sensor or the cable. It's a little bit larger than a bubbler, so debris could get caught on it, which would require higher maintenance to clean it. And temperature could also affect a pressure transducer. So if you had it in a dry channel and then, for stormwater monitoring, then you had cold water go over the top of it, it could create a slight shift in your level reading unless your sensor is pressure compensated or calculated. So let's move on to methods to calculate flow. You need a primary device, which I'll talk to you about in a minute, and it uses a level to flow rate calculation. And so we can use the level devices we just spoke about on Weirs and Flumes to give us our level to flow rate calculation, also known as a lookup table. Some of the common level sensors that are used with Weirs and Flumes are going to be the ultrasonic sensor we talked about, the radar level sensor, the pressure transducer level sensor, and the bubbler level sensor. Now, a primary device that I mentioned could be a weir. And what is a weir? A weir is a dam that's built across an open channel which the water flows over. They can be made of metal, concrete, or wood. Flumes are specifically shaped channels made of fiberglass or concrete. So the size of the flume is dependent on what your expected flow range is. So what's needed to measure an open channel flow? You need the primary device, which is the weir or the flume. So here we're looking at a weir, and this is an example of a flume. The secondary device is going to be a flow meter, which the flow meter is then connected to one of the level sensors we spoke about. Now let's first talk about the weirs. So some of the things you need to know about a weir is the sensor placement. So we need to know the measurement point is, and all these settings are kind of dependent on what the expected flow rate is through this particular channel for your weir, and that's going to depend on the where you're going to place the level measurement, which will be 2 to 3 times the maximum expected head height going over the weir. We want to make sure that's far enough upstream to avoid the drawdown effect, because if you have it too close to the weir plate, you're going to get that drawdown, and it's going to give you a slightly lower level, which is again incorrect flow rates. Now the height of the weir is going to be, you want to make sure that's 2 to 3 times higher than what your expected maximum head height is. And once again, these all go back to what you expect your flow rate was going to be to determine what the maximum head height is. And the biggest thing is we're calculating the amount of flow going over the weir. So when we set the calibrate the level for this, you notice where the arrow is at in the dark blue. We're concerned about that level going over the top of it. So the 0 point on calibrating level on a weir is going to be at the top of the weir. Now here's an example of a common weir type, a rectangular. And with this one, you notice it has a staff gauge on the side of it. And so that staff gauge is set to the 0 point at the top of the weir, the crest of the weir, to make it easy for calibrations. This one we're using a bubble tube to read the level, which you could also use an ultrasonic sensor or a radar level sensor to read the level and calculate the flow. Other types of weirs are going to be a V-notch weir. They come in very handy for low flows. The weir size is going to be dependent on the expected flow rate through there, and the height of the crest to the bottom of the channel is also going to be dependent on how much flow you expect to go through there. Now, where are the weirs used? They can be used at the effluent wastewater treatment plant. It can be used for industrial discharge, and in this picture, showing that it's being used for stream monitoring or monitoring the flow through this ditch. Now, what are the advantages? Lower cost, because they can be made out of metal or wood, concrete, and so they're easy to design. You have a rectangular channel with or without contractions on it, a V-notch channel. Depending on what the expected flow rate is going to help you determine what type of weir you want to install. And the weirs can be used in large channels or small channels, as you saw in the previous pictures. The disadvantages is that you do have the head loss because the water backs up because we actually have a weir plate or a dam in the flow stream. So what does that mean? It's not suitable for flows with solids. So if we have debris going through there, it's going to get caught up on that weir plate, which is then going to lead to maintenance. And depending on the size of the weir, you may have to use some large equipment to clear that debris out of there. The accuracy of a weir is going to be dependent on the approach velocities. If the water is moving too fast through there, it's going to go over the top of the weir too fast, which will then have an effect on how it reads the velocity. Another disadvantage is the design of it. So even though it's a simple design, you still need to get a civil engineer involved to help you determine what size of weir you need to put in, and where it's going to be installed, and how that's going to be designed. So installing a weir, may take a little bit of time and money to install because there's construction involved to actually build this weir across your channel. Now let's move on to flumes. Things to know about a flume. There are three components to a flume. You have the converging section, which is the inlet to your flume. This is where you're going to measure your level using an ultrasonic or a bubbler or a radar or even a pressure transducer to read your level to calculate the flow rate. The throat determines the size of your flume. So you just measure across it. If it's 3 inches across, you have a 3-inch flume, in this case, a par-shell flume. And then you have the diverging section. This is where the water exits the flow stream, and we should have free flow going through the diverging section of the flume. Next, I want to show you some examples of some common types of flumes. What we're looking at here is a par-shell flume, and as you notice, it's using an ultrasonic sensor to read the level for the flow calculations. This also has a staff gauge built into the side of it to make it easy for on-site calibration. Next, we have a Palmer bolus flume. The nice thing about Palmer bolus flumes is that, like in this example, we have a 8-inch pipe going through there. You can purchase these as an insert. So in this case, they cut out a section of pipe. They're using couplers to attach the Palmer bolus flume into that channel. So it makes a nice, easy installation with accurate flow readings. Other types of flumes you may see are a trapezoidal flume. These are great for when you have really low flows, and they could potentially get higher flows. As you notice, the bottom of that trapezoid is very narrow to accommodate the lower flows, and as it opens up, it can handle the larger flows. And again, this has a staff gauge built right into the side of it. Other flumes you may encounter are the H flume. The nice thing about the H flume is you can use this in applications where you don't have the necessary downstream straight pipe afterwards. As you can see, this is just free falling onto the rocks, so it's a good option when you don't have an ideal application with the proper straight run upstream and downstream. So where are the flumes used? Typically they're used at the influent of a wastewater treatment plant, stormwater discharge, and industrial discharge. So why are they used at the influent of a treatment plant? It's because flumes can handle some solids. They do require some cleaning, but the idea of a flume is that when it goes through the restriction, the throat, it accelerates the velocity going through there, which helps make it essentially self-cleaning. But there will be some maintenance required depending on what happens to go through that channel or if it becomes surcharged. Now, what if you don't have a weir or a flume? How am I going to measure flow? So without a primary device such as the weir or flume, you may come across round pipes or rectangular channels that you have to monitor. And to measure flow in a round pipe or rectangular channel, we need to know the pipe size. In this case, it's a round pipe. We need to know the depth of the water, and which we're going to use that to calculate the wetted cross-sectional area. And then we need to know what the average velocity is so we can calculate our flow, area times velocity, to give us our flow rate. Now first, let's talk about some ways to read the velocity. One way is a propeller point velocity sensor. It's a simple device. You put it in the flow stream, and the propeller turns proportional to the speed of the water to give you a velocity. Now, this does not have a level sensor on it, but it will tell you what the velocity is. Other ways to read the velocity is a magnetic point velocity sensor, and this produces a magnetic field about the size of a tennis ball in front of it, and it will produce a voltage that is proportional to the velocity going across it. And these are commonly used to profile a flow stream. And so you may take this device and put it in 9 different places in your flow stream to come up with an average velocity. Other velocity measurement meters are known as the pulsed or gated Doppler. And the way this works is you have a sensor in the bottom of the flow stream, and it transmits a sound wave, in this case, a narrow acoustic beam all the way through your flow stream. And each one of those little segments, it will read the velocity at each one of the segments. So what it's doing is you're able to profile the entire flow stream, and it will read the slower velocities towards the bottom of the channel, closest to the wall. And then as you get towards the surface, just below the surface, you're going to see it's going to read the highest or peak velocity, and it's going to average all those segments to give you a velocity reading. Other ways to read velocity are the multipath transit time. And this works is you have parallel paths mounted in that channel, transmits the acoustic sound wave, and it is measured on the sensor on the opposite side. And this can read both forward and reverse velocities depending on the frequency shift that it sees when it transmits the signal. Other common types of velocity sensors are the continuous wave Doppler sensor. And with that, it uses the area velocity equation to come up with our flow rates. And with the continuous wave Doppler, it has a pressure transducer to read the water depth, which will give us the wetted cross-sectional area. It'll transmit a frequency, like a 500 kilohertz frequency, measures the average velocity by reading the frequency shift from the air bubbles and particles in the water to give us a velocity reading. And with a continuous wave Doppler sensor, you can read both positive and negative velocities. So it will determine which way your flow is going. Now, the advantages of a Doppler sensor are no weir or flume. because we can use this in a round pipe, rectangular channel, streams. So there's no need to estimate the slope or the roughness because we're actually reading the velocity of every flow stream. Profiling is not required. However, there are a lot of people that prefer to profile their flow stream and come up with a coefficient based on their profiling. And then with the area velocity sensor, the Doppler velocity sensor, you can use that in open channels, submerged pipes, even full pipes, surcharged and reverse flow. It's a very universal sensor that allows you to use it in a lot of different applications. But there are some disadvantages. As far as the debris or silting over the face of the sensor, with a pressure transducer, it can read the water depth. However, it could have problems reading velocity if it has silt or debris over the sensor. Swirling in front of the sensor is going to create poor hydraulics, which could end up reading both positive and negative velocity at the same time because of the swirling. Now, some common types of other common types of velocity sensors are the non-contact velocity sensors. So some that are on the market are the laser sensor, the radar velocity sensor, and the ultrasonic non-contacts can be used to read velocity. So first we have the laser subsurface velocity sensor, reads below the surface of the water, and then the other types are going to be the radar surface velocity and the ultrasonic surface velocity, which I'll talk about in the next few slides. So the first non-contact radar is the radar sensor. It reads the surface of the velocity and then is adjusted to estimate the average velocity. And with the non-contact, it's using an ultrasonic sensor to read the water depth and then the radar to read the velocity. And as you can see here, with this radar sensor, it needs ripples on the surface of the water. You know, it needs a little bit of surface turbulence to get a return signal off the surface of the velocity to get a velocity reading. Other non-contact velocity sensors are the ultrasonic, and it uses both ultrasonic level and ultrasonic velocity to read the velocity. So this sensor is mounted in the pipe, where the last one is typically mounted like above the pipe in the chimney. So this will use the ultrasonic sensor to determine the level of the water, calculate the wetted area, and then it uses the ultrasonic to bounce off the surface of the water to get a return frequency shift to determine the velocity of the water. And last, we have the laser flow sensor to read velocity as a non-contact sensor. And the way that operates, it also uses an ultrasonic sensor to read the distance to the surface of the water. Once it knows the distance to the water, then it can focus the laser below the surface of the water. And what we're looking for is it's going to read the peak velocity below the surface of the water to then calculate what the average velocity. And while that laser's on, it's on for 2 seconds. It takes 5,000 Doppler readings to come up with its velocity reading, and it's capable of reading up to 15 different points below the water surface. So how does that laser work? You know, a typical laser will just point out to infinity. And so with the laser sensor, what we do is there's a lens built into the sensor. The laser diode is then moved back and forth to focus the laser below the water surface to get the strongest return signal. And then that focused energy is then redirected back into the laser flow sensor. And so then the laser can actually focus at the several points below the surface of the water, and it takes the 5,000 readings to give us our strong velocity signal back. And with the laser sensor, it can also determine the direction of the velocity. So based on the frequency shift, And as the water is moving towards it, it's going to see a faster frequency shift. If it's moving away, it's going to have a slower frequency shift to determine the velocity of the water. Now, where can the non-contact sensors be used? So any of those can be used in small channels or large channels. What you're looking for is just uniform flow coming through either of those channel types. They can also be used in stormwater applications, natural channels. Why non-contact is a great option for these type of applications is because in a storm channel, you don't know what kind of debris is going to go through there. Shopping carts, bowling balls, any in-pipe sensor has potential to be damaged or even torn out if it's in a stormwater or a natural stream application. So the non-contact is a great choice for that. So what are the advantages of non-contact area velocity sensors? Is the no flume or weir is required. Minimal civil engineering work is involved because we don't have to design the weir or the flume. We just simply need a straight channel of pipe to install your sensor. The safety, if you can keep the field crews from having to get into the flow stream, they're going to be a lot safer, especially now with the COVID-19. The fewer times that you have to touch the water, the better. Because it's non-contact, you can have lower maintenance because you don't have to worry about cleaning debris off the sensor. The installation is going to be easier because you don't have to stop the flow. And then, and they also measure both open channel and reverse flows in your channel. Now, some of the disadvantages of the non-contact is going to be the turbulence or a non-uniform flow, which for any application, you want to have the uniform flow to get accurate flow readings. They're not suitable with thick surface foam because they have three we were just talking about, the ultrasonic sensors to read the water depth, and the foam could have an effect on the ultrasonic signal. Steam can also have an effect on the ultrasonic signal. Now, the radar and ultrasonic sensors, the surface velocity may not accurately represent the velocity, especially if it's an outdoor application where the surface is actually being affected by the wind. That could give you an inaccurate velocity reading. Now, what are some other considerations? You need to determine if it's a hazardous area installation. If it is, you need to pick the appropriate intrinsic safe rated sensor for your application. What are your performance requirements? Is it repeatability or accuracy? So with the repeatability, we want to make sure that every time the level goes to say 6 inches, we get a repeatable flow rate and velocity. It goes to 1 foot. Again, we're looking for the repeatability, possibly for flow pacing or dosing. Now the accuracy, that's going to be more for billing applications. So you want to find the most accurate flow meter for your particular application. And then what is your flow profile? If you have, do you have uniform flow? Is it the flow a little bit distorted? If so, then you may want to pick multiple velocity points to give you more accurate flow reading when you have distorted flow profiles. And last, looking at your application, some of the devices have street level removal tools, which then allow you to put a pole down that manhole riser, remove the sensor if needed. So you can either move it to a different location, or if cleaning is needed because it was submerged, you can pull it out and easily install it. So which flow meter technologies should I use? I've shown you a lot of different technologies that are out there, and no one technology can be used for all applications. That's why there's so many different ones on the market. So your decision is going to depend on the following. Do you have a Weir or Flume primary device already installed, or are you planning on installing one? Is it an open channel? What's the accessibility? Do you have easy access to get to the sensor for maintenance, for cleaning if needed? And what are your performance requirements? Are you looking for the highest accuracy, or are you just looking for flow trends? and last, is it hazardous location rated? You know, do you need an intrinsically rated sensor? You know, if so, you know, make sure that the sensor is rated for your application. So with that, I thank you for your time. I want everyone to stay healthy and safe. And if you have questions, please submit them right now, and I'd be happy to answer them for you.
Darrell, we do have a question.
Okay.
And it is for the wave Doppler, does it operate accuracy no matter the install position along the pipe interior? The illustration that was shown is at the 6 o'clock position.
All right, that's a great question. So as far as the continuous wave Doppler sensors, traditionally they're mounted at the 6 o'clock position in the pipe, but some applications that are known to have debris or silt on the bottom of the channel require the sensor to be rotated off to the side to avoid any of the silt buildup on there. So as far as it's still going to read the level accurately. So you know, if your water depth was 6 inches, you rotate it up off the side, you're still going to calibrate the water depth to 6 inches, and then it's still going to be able to transmit that continuous wave Doppler signal. The trick to it, though, is that we want to make sure that you still have, you know, about an inch of water over the top of that sensor to get a velocity reading. But as far as, I don't have exact numbers, but the accuracy isn't going to be affected very much by having it rotated off the sensor, off the bottom of the channel. Now, another question that came in regards to the Doppler sensors is that what happens if the pipe goes full, it's surcharged? Well, you're still going to get accurate flow readings from that, because what happens is that when the pipe goes full, the level transducer is going to recognize that the pipe is 100% full, so our area is going to be at 100%, and then at that point, the velocity or the flow rate will be proportional to velocity. So you continue to get accurate flow readings, and it can read the reverse flow if it starts going backwards.
Another question, Darrell, is what is typical depth of laser beam?
The typical depth of the laser is, it will read at, it depends on the actual water depth, and it reads at a percentage below the surface of the water. So it will read at 5% below the surface, at 8%, and 11% below the surface of the water. So if I only have 1 inch of water that we're reading, you know, at 5, 8, and 11%, it's going to be, you know, very close together. If I have, you know, 5 feet of water depth, well, then they're going to be spaced out a little bit more. And let's see, what's our next question here? Give me a second. Let's see, would you choose the pressure sensor to start a composite sampler in a manhole? Sure, you could use a pressure transducer to start a sampler. So you can do two things with it. One, you could trigger your sampler just on depth. Like if it's an ISCO sampler, you can tell it that my water depth is greater than 6 inches. It can start the sampler program. And then you could also use it to calculate flow through that channel. So you could, one, start it on depth, and then you could flow pace your sampler after that. Let's see, another question. Which technology works best for gravity flow sewer pipes, meters installed in manholes? So as far as a gravity flow, I would use one of the velocity sensors we talked about, either like the continuous wave Doppler or pulse Doppler or the non-contact velocity sensors, because they're going to be able to read the depth to calculate the area, and they're going to be able to read the velocity. So we aren't concerned about the slope or the roughness. And then with the gravity flow meters, you know, like I said, they'll read the velocity and give you accurate flow readings. see. Another question is, will the recording be available on our website? Yes, we will post that on the website. And Sharon, when do you think that will be ready, like in the next week?
Yeah, within the next week, and more than likely it'll be sooner.
Okay.
Are you also
Right.
seeing the questions in chat?
Yes, that's what I'm looking at right now.
Okay, perfect.
Let's see. What is the best option for open channel flow measurement in cold weather conditions? Yeah, with cold weather conditions, that can be a little bit tricky because of the, depending on how cold it gets. As far as the bubbler, that works well because it isn't affected by the steam that could potentially come off the water. And as far as it's just putting dry air into that flow stream, so the bubble line itself won't freeze because we don't have any water in it. It's actually putting out just air. And then as far as the non-contact meters, I've seen them work very well even in very cold conditions. The only time one time I've been aware of that there's been some problems in really cold conditions is that a non-contact sensor outside in a blizzard, there was just so much snow going past, it was causing trouble with the ultrasonic and then actually blocking the signal to read velocity. Let's see. Another question came in, is it critical to install a stilling well off of Flume to measure the flow? No, stilling wells are not required for it. They do make it easier, as far as installing a level sensor and taking a level reading, because the stilling well by design creates a nice smooth surface to give you the average level, but it is not required. And in fact, I see a lot of applications don't have the stilling well. Let's see. Again, another question that came in about we've have a laser flow sensor and rectangular channel. The sensors are installed after a gate. We're presenting a reverse flow phenomenon, which the gate produces turbulence. Yeah, so the biggest problem is that the gate itself is creating turbulence. So what we want is uniform flow going through that channel. In this particular application, pointing the sensor downstream to try to give it a extra distance to minimize some of the turbulence could help out, or worst case, it just has to physically be moved to a different location with uniform flow. Let's see, another question is, let's see, as far as contact sensors, I'm currently using a flow tracker. It's having difficulties giving accurate readings in shallow channels. Is there other equipment that you suggest? Yeah, as far as the laser flow sensor is a fantastic meter for low flow applications because it can read all the way down to a ½ inch of level and a ½ foot per second of velocity. So it's capable of reading really slow flows, low levels accurately, and then also read the high flows. And another question about the laser flow is, does the level of turbidity affect the laser velocity readings? No. Well, generally, no, it doesn't. As far as We can use the laser flow sensor in effluent water, which is fairly clean. And in fact, we have a test running on a mining application, which is very turbid water, and we're still getting accurate readings through that very dirty water as well. Let's see. Next question, what can I do if I'm not getting good downstream readings under submerged conditions through a partial flume? So as far as, yeah, if you don't have good downstream conditions, what's going to happen is you're going to end up over-calculating your flow, because if it's starting to get into a submerged flow condition, it isn't free-flowing through there, so which means that water level is going to be slightly higher. And so using a flume is just a level to flow calculation. If we get higher levels, we're going to have higher velocities. I do not have the formula handy, but yeah, you may want to install a level sensor on the essentially the upstream and downstream to determine when it's going into a submerged condition to come up with different flow conversion when it's in a surcharge. Let's see, what else do we have? Let's see, to measure level around 2 meters, which is better, radar or ultrasonic? As far as only 2 meters, actually you could use either one, the ultrasonic or the radar. I wouldn't really say one is better at 2 meters. If it was 3 meters or higher, then the radar would probably be better. But as far as an ultrasonic, would work just fine within 2 meters. And we got another question about we have a low pressure system, force main that discharges into an existing sanitary sewer. It needs to be measured accurately for billing. So as far as sanitary sewer for billing application, the laser flow sensor non-contact is been used quite often for billing applications because it's going to be within 4% for the flow rate accuracy. Especially since it's a sanitary sewer, the non-contact is nice because you're less likely to have problems with the debris getting caught on an in-pipe sensor, which can then back up your flow stream. So the laser flow would be a great option for those billing applications. Let's see. I had a question about are there any types of waste that cannot be measured accurately by laser meters? Well, as long as we have uniform flow going through the channel, we can read it. That's kind of the key to any of these flow meters is making sure we have uniform flow. So if we had a lot of solids going through there, which was creating a non-uniform flow, that would be a problem. And let's see, what are the best options for low flow situations with possible solids and debris? Kind of touched on this already. It's the laser flow sensor is going to be great for low flow applications. Just because it can read down to a ½ inch of level and velocity. And then, as far as having it non-contact with the solids and debris, we're less likely to have issues with that. Let's see. What's the lowest velocity that can accurately be measured with a Doppler sensor? What I've found over the years with the Doppler sensors is around 0.3 foot per second is about as low as I'd want to go. But I'd prefer to stay around 0.5 foot per second or higher with the Doppler sensors. You know, one of the issues that you can come across with slow velocity is that, you know, sediment starts to fall out of the, it's no longer suspended when you get less than 2 foot per second. And so then, you know, you tend to run into issues with maintenance where you start having debris collecting on top of the sensor. Let's see. What's the best option for a flume with heavy turbulence in the converging section? Adding a stilling well in this particular application would help because then that's going to give you a more accurate or average level reading. So then you can use a bubbler or an ultrasonic. But if you do not have a stilling well, I would use the bubbler. I think you're going to get more accurate level readings out of a bubbler than you would an ultrasonic for turbulent applications. Somebody else is asking about what's the recommended maintenance schedule on laser flow units and what does it involve? So as far as that's a tricky question as far as on the maintenance schedule. We do not have a specific maintenance schedule that we recommend for it because it's all site specific. So if you have an application that's you know, tends to build up debris in your channel, you're going to have to go and check on it more often to calibrate it. If it's a site that goes underwater once a week, then you're going to have a more frequent maintenance schedule. But by design, being non-contact, it's minimal maintenance. With that being said, I would recommend at least checking on it twice a year, if not more often. But usually the maintenance schedule is just dependent on the application and local regulations on how often you need to go out and calibrate it. Let's see. Another one is it feasible to set up a laser flow sensor in the entrance of a street manhole for short periods of measurement times? Yes. So in fact, we have several communities that they'll buy a laser flow sensor and then they'll buy the wall mount bracket, and they'll just mount the bracket in several locations throughout the collection system. And so then that allows them to go over there, use the street level tool, set the laser in place on the bracket, you know, take your readings for a day or a week, and then remove it and move it on to the next location. So yeah, it's possible. And as far as mounting the wall mount bracket to the wall, it's 2 anchor bolts. Doesn't take the crews usually very long to install it. It's fairly easy. Next question, in an effluent flow meter application in a round pipe, the water is apparently so free of debris that a 350 Doppler velocity sensor can't get accurate results. Would the 360 laser flow sensor be subject to the same problem? What I've found is that the laser flow sensor is able to read in applications that the continuous wave Doppler sensors have not been able to read. As far as the laser, when it's on for 2 seconds, taking those 5,000 readings, we've been able to read some very clear water. In fact, a lot of people I've worked with over the years that have created their own flow benches, they're just using tap water in their flow loop without having to add anything to it, and they're getting accurate velocity readings. What you'll see is the Doppler signal that's reported from the laser flow sensor. The Doppler signal is going to be lower, but as long as it's over 1,000, we're getting accurate velocity readings. The Doppler power, Doppler signal, it represents the amount of turbidity particles in the water. If you have dirtier water, you can see that the Doppler power is going to go higher. Cleaner the water, it's going to have a lower Doppler signal. Doesn't mean that it's better or worse, it just means that we just have more or less particles in the water. And let's see, we have another question. With velocity of 3 foot per second in open channel, excessive slope, would the laser meter flow depth and velocity accurately measure flow less than ½ an inch? Well, as far as our specification goes down to ½ an inch, I have seen it in applications where it's been slightly lower levels and still getting accurate, level and velocity readings. It just becomes really a little more tricky on the installation, because if you do have a steep slope, you may want to install the laser parallel to the channel to get a better level reading. And then we do have the option in there for adaptive focus to help us for applications like that, where it is a little more tricky to get that velocity reading. So with the adaptive focus, it's automatically going to scan the laser up and down 3 inches to find the maximum Doppler signal. Another question is, how are these velocity meters powered? Can solar or line power be used, or a specific battery pack? As far as the ISCO equipment and other velocity flow meters, yes. So the answer is yes. You can use AC power, and most of this equipment just uses an AC to DC power converter, which means that if like the ISCO meters operate on 12 volts DC, which means you can use a battery, you can use solar power. The signature meter has special program settings, especially using on battery, to reduce the amount of power it's using for the display. So yeah, you could use it on solar or batteries. Let's see. How important is the placement of the laser flow sensor at the effluent discharge point? Well, the important thing about the placement is that we just need a straight channel pipe with uniform flow. That's the biggest thing, is the uniform flow through that channel. So if it's slower moving velocity, you might not need as much straight run of pipe as you would for higher velocity, because if there's a bend or an adjoining pipe upstream, we have high velocity, it's going to create a lot of turbulence. But as long as we have uniform flow, that's the key for any velocity sensor. Somebody's asking about how the temperature will affect a sensor, pressure transducer, if you had it in a dry pipe. So depending on the sensor, if you have it in a dry channel, say for a stormwater application, it's sitting at the ambient air temperature, and then when the colder rainwater goes over it, sometimes you can actually see a shift in the level readings. So if the temperature sensor is not in the built into that sensor, what is usually required is you have to take the pressure transducer, put it in the water for 5 to 10 minutes to let it acclimate to the water temperature, and then you calibrate the level. Yeah, what I found, you normally don't see a really big jump, but you may end up with possibly an 1/8 to 1/4 inch jump in level when you go from a dry sensor to a wet sensor. Let's see. Another question came in is, which non-contact sensor is best for level measurement in a tank, ultrasonic, laser, microwave, radar? So as far as tank monitoring, the ultrasonics and the radars are the most common ones that I see. I don't have any experience with the microwave. Well, I guess that would be the radar. Yeah, ultrasonic and radars work quite well for level measurements in tanks. And depending on what's in that tank, if you do have, like a layer of oil or something across the tank, the radar sensors can actually be programmed to ignore different viscosities of the water to ignore the oil on the top and then read just the level. Well, that is about it for the questions today. If you have further questions that I did not answer or didn't see yet, please email them to me. You still see that on my screen. It's Darrell, DARRELL Kuta, KUTA, at Teledyne.com, or just respond to the email that Sharon had sent out earlier, and I would be happy to answer your questions.
Thank you all for attending our Open Channel Flow Measurement 101 webinar today, and thank you to Darrell for presenting on this topic. As mentioned, it was recorded and a video will be made available. If you have any questions regarding this webinar, please feel free to reach out to me through Zoom and I'll forward it along to Darrell. I also have all of the chats and question and Q&As recorded, and we will try to reach out to you to provide answers if they were not during the webinar. Also, if you would like a certification of your attendance is desired, please feel free to email me and I would be happy to provide this. Thank you again for joining us. Stay healthy and have a great rest of your day.